words of peak data rates, which one takes the peak in terms of data rate, the user effective efficiency, mobility. So mapping about this in the three-dimensional, about the various factors of 5G. So this is about the three parameters like massive time machine communication or URLC or all those things are just picture over here. And this explains you that how much fast are you going to utilize over it, whether you are going to exploit the situation. No, as an end user for this, I am going to use that 10 times, the latency is going to reduce. So as low as 1 millisecond. So 10 times the connection density is going to increase. The throughput is going to be 10 times of the continuous thing with respect to gigabits. I am going to look over it. And efficiency, traffic capacity, network efficiency, you can just going on to increase over it with a less latency. But whether exploitation from our end user is very big question mark of effective utilization. Next please. And this shows that how much by utilizing, how much days we are saving of power, the device, how much time it explains it. The owner of an indie slice can tailor speed, capacity, coverage, encryption, and security. That's a very big significance of the 5G, which we talk about in network slicing. Next please. So these are the various factors like software-defined networking and all those things. We are just looking over it, network slicing and 5G core. So this is the network architecture. When you discuss over it, we have some, like as I said, three high bandwidth with low latency with a low data rate. So smart cities, autonomous vehicles, connected vehicles. So there about the self-driving cars, which plays a focus about it, and about the better cloud management with respect to more UAV, unmanned aerial vehicles. So sports broadcasting, all those things are continuous video transmissions are looking over it. So that's been the various use. Next, based on it, we just move on to Internet of Things. As you all know that if the networks are getting connected, which is going to be a node of collection of things, physical objects that contain embedded technology to communicate and interact with the external. One in terms of sensor plays a major role, and next about the how about the power. And how about this frequency in terms of wireless connectivity? What type of frequency I am going to use over it? When I am going to use over the frequency, the collection of data are going to be a major part. If the data are collected, where it is going to be stored, or in terms of cloud, or in terms of fog computing utilization, or in terms of edge. We talk now discuss more about the edge computing in order to reduce the latency, in order to make faster decision instead of waiting for the cloud to take a decision to come over it. So edge computing plays a major role over it. And then how it's going to be. So in terms of utilization. So that's about how we call any time, any place, anyone, whatever thing we call for an IoT. Next please. So this is about the four basic pillars. The people, the data, the process and the things. So this is about what we call about IoT, which we discuss about anything in discuss on parameters. Okay. So here is of IoT which covers about it. Feeling the things that about sensors and wireless sensor networks, about minimization, embedded systems, how it is going to be the processor, how it is going to be overlaid, it's an one-to-one internal work to be looked over it, and identification of things, how it is going to be used for and tagging the thing. Next please. So this is about how this explains about the parameters which I will discuss over it. I just skip over this. And next please. Next. Okay, so before getting on to the next step with respect to the futures and implementation, I just want to touch about this knowledge management triangle or pyramid, which talks about basically from data, that talks about information, knowledge, understanding and wisdom. We know that how, what, for what, we know that come across it, how effectively this information, whatever we get, as you know that data is plenty, but from that what you infer, how you collect, what you want to transfer, how the knowledge is getting to be converted. That plays a major role over it. So that explains about from symbols to answer who, what, where, and for all questions, and about evaluate understanding. So that's about the data are created, but how it is going to be understandable to the end user. That's about the understanding and wisdom people can obtain about it. So that's about the knowledge management, turning data into wisdom. More important, how we analyze, how we looked over all those things. Okay, the data analytics plays a major role in it. Next please. So this is about the futures, which talks about the dynamic future, intelligence, energy, safety, various parameters. In same terms, the challenges are there, the parameters to be looked over it. So the key drivers in terms of it, whenever we say any technology, there will be a platform which is going to be inactivated, so which becomes an active to involve over it. So that's about infrastructure, whatever connectivity in terms of it, how the data are going to be stored, like computing, what types of computing, where the data are to be stored, how I'm going to recover over it, and the process excellence, architecture. We know that we talk about OSA layers and TCP IP layers, IP version 4, IP version 6. When you talk about it, how it is going to be looked over in the connectivity in terms of communication technologies. So that's about the architecture assimilation, then technology adoption. So when a conversion from one technology to another technology, how it is to be enabled. So we call technology enables compatibility. So all those factors are getting into coverage, and how I'm going to leverage the data, how I'm going to deploy it in terms of internal and external. That's about the next things we're looking over it. Next please. So when I talk about it, I touch about the architecture. As I said, we will be discussing about the architecture in terms of IoT and also for IoMT more specific, we'll be focusing. So here we can see that there are 7 layers are being given basically. So starting from physical devices from lower layer to connectivity, edge computing, data accumulation, data abstraction, application. So it goes on to the differentiation things like from things, how it is going to be leveraged, as we have discussed basically from physical layer to application layer from OSI and TCP IP. Similarly, we just about this IoT World Forum reference model, which shows about the 7 layers. Okay, so that's the things layer, which talks about the things which is going to be connected, the sensors, RFIDs, and all those things. The network, which plays a major role, which talks about its communication technologies that even very specifically called as low power communication technologies. We talk about Zigbee, Wi-Fi, Wi-Fi. Okay, then about Bluetooth, near power communication. We'll be touching about it. Then about the middle layer, which talks about the computing, where all the computing parameters are taken care, and about the application, where it is going to be for an end user in terms of agriculture, healthcare, industry, automation, various any factors are looking over it. So that's about the application. So we have an example also for it, where we have different parameters, agriculture. Please keep it up. Okay, so IoT structure for a smart agriculture, it shows about a farm is being given where the moisture is being checked over it, what is the temperature is being checked over it, any alarming issues, anything which is going to be checked and intimated the data has to be the concerned intended user, how it will alarm, what repeated either water to be sprinkled or if it is so dry or if it is too high, what it is to be looked over it. So you can see the things in terms of soil, we have different types of sensors like soil moisture, ultraviolet, air humidity, temperature. In terms of things we have sensors. In terms of communication, the technologies which you are going to use wirelessly. In terms of middleware, what type of communication like gateways. So this explains about how this is going to be mapped in terms of all the layers of all those things. That's about the structure of a smart agriculture area. And this is about the connected IoT. Next please. So next, this is what we want to focus more about it. Low power communication devices. So this is very famous symbols we come across in life. Whenever we go for any applications, whenever we go for any hardware projects and all, our students or ourselves, we just get, in order to come across these names and all very frequently. Zigbee, narrowband IoT, like low range, LoRa, Wi-Fi, Sigfox. When we discuss over it, we can see that everything has a specific frequency over which it can able to deliver the data rate or in terms of frequency or in terms of distance. So that's the 2 criteria which we are going to look over it. We can know that whenever we go for smart cities or smart home appliances where the power is very less, the distance is going to be very low. So I'm not going to transfer my signal for a longer range. So that means I can able to reduce my power range. I can able to lower my data rate. So which is going to be happen then. So the recharging facility of the device is going to take place very rarely instead of 1 per day, or so that's basically the power consumption becomes less too. So that's about, we can see that the next flag diagram, it shows that the technologies, the power, the transmission ring, data rates. So we come across basically Sigfox or Zigbee. Whenever you go for home automation, we can come across all those things, the smart cities application, home monitoring system. You can see that in Sigfox, you can see that the corresponding thing Zigbee or with respect to 10 to 100 meter with respect to low data rate. I don't want a high data rate in megabits, it's just only 20 to 250 kilobits per second, which is having a length of 10 to 100 meters, which is less than, so that we can able to low data rate, which is going to be Zigbee, we can look over it. So in terms of based upon the Sigfox, we can see that 100 to 600 bits per second is going to cover about 3 to 50 kilometers. So based upon a situation, I can able to decide what type of an low power communication technology I can look over it. So that's a basic thing which more focus is based upon the selection of the technology. Like it is going to be the scalability, range, how it is going to be the Sigfox with respect to how it is going to be performable for range, the coverage. This chart projection shows that which acts best over it. Next please. So that's based on it. We just move on to IOMT, Internet of Medical Things. When we touch about it, we would have covered across telehealth and telemedicine. So far, in how the data are going to be monitored, and from it how it is going to be. So now we can look about it whenever we talk about such type of devices and data. We talk also touch about like in technology enables like blockchain. Now blockchain plays a major role in disruptive last 4 to 5 years. This is one emerging area. We can see that recently many state governments are started implementing the blockchain technology for any registration documents also, but to avoid forgery and where are the connectivities of vehicles and all those things. The blockchain is going to be the certificates, documents, validity. So we can see that however the records whenever are getting to it, somebody is going to monitor a record, how secure over it, how it is going to be so safe, how it is going to be potential threat for us. So that's basic thing. The privacy and the security comes to the factor over this. So that's about the telehealth, digital information communication, access healthcare services remotely and manage healthcare. So like doctor communication, diagnosis, ongoing monitoring. So it's about telehealth and telemedicine. Now we just move on to IOMT. Next please. So that's about Internet of Medical Things. So everything is clubbed into for medical devices. In terms of monitoring, in terms of measurement of the human parameters, we go for it. Nowadays we just start using, everybody start using the Fitbits or health watches or whatever thing, whether how much distance I am walking, how much calories I burn, whether I am taking regularly water, whether the temperature, or in terms of SpO2. So many of them would have not taken much serious about. Once the COVID has come, everybody started to take like a temperature, either 99 or 1 or 2. What is my SpO2 level, 96 or 100? If something comes to 92, we are put into alarm condition that we are been into trouble. We just try it 1 time, 2 times, we check it properly, where machine is working or our health. So the parameters are monitoring, that's very sensitive. Your health is okay, but the device is not properly functioning, means that becomes a very, a villain climax is going to come for us. We are very okay, but whatever the dust comes over it, we are put into trouble. So that's the device, how we are going to perform, how we are going to ascertain, how the device is going to be checked, how it is going to be looked over it. So that's a very critical issue. There's majority doctor, instead of devices, they just always they have a suspicious eye about this output of the device given concern. Because they go and seal and feel and touch and see the pulses and all those things, rather than giving some data. So I have a software to see that it predicts. That's all different, but unless and until they haven't trust over it, they don't have to have taking risk over it. So that's basically we call about it Internet of Medical Things, where wireless remote devices are connected, where it's going to help for a human assistance. Okay. Next, when you are getting over it, next please. So you can see that like a health app, like what Fitbits, clocks. We are having various things. As we have then various, like we come across a technology called body sensor networks, BSN. Okay, body sensor. We have some devices which are placed on the body, in the body, over the body. Okay, whether a smart pills, we just inside the water, we just swallow and check it out whether it is something is placed on our body or something is going to test on our body. Similarly, we are just going to see that how these things are going to be monitored and looked over it. Next, please. So that's the thing which talks about the patient engagement. Next. So here it shows about the chart which I want to highlight about it. The global Internet Medical Things market research. So it shows that cumulative annual growth rate 2023-2031. It's about only North America. It shows how much fold it is going to increase. And here it shows that from 2021 to 2028, it's going across various countries like Japan, South Korea, India, China. The market, how it is going to be increased in terms of 40,977.84 million by 2028. So there is going to be a huge market. When we talk about the market, we always think about not only in finance or whatever thing products. It has a basic impact of research. It has a basic impact of production in terms of R&D, in terms of service, in terms of interdisciplinary approach where will be utilization of all parameters. So there is going to be a huge future over it, which we should be keeping an eye over it. So that's the thing which I want to highlight over it. That's about the market, which shows over the prediction of 2028. Next, please. And this is, I have taken from an article from Science Direct, which shows about the various aspects in terms of like a key enabling technologies. Please, next. So this is about the IoT components, how the patient is being monitored by the physician, how he is going to get in control, how it is going to be indicate anything, alarm situation comes over it. Next, I just skip it over it. Yeah. So this is about the architecture, which is more focused about IOMT. As we come across it, we have a perception layer, we have network layer, application layer. We have that we know that whenever you call for it, like an TCP, OSLA, we come across like different sublayers are there. Okay. Similarly, we have a data acquisition in terms of data access sublayer, the network transmission, network service, then medical information decision making in terms of application network and perception layer, then basically data source. So here the previous slide. So the perception layer talks about the basic layer where it's a bottom layer which has data access and sublayer data acquisition. So one acquisition in terms of how the signal is going to be acquired or taken input. That's the acquisition. In second one, it talks about what type of range of the network communication technologies, either in terms of Zigbee or Wi-Fi or LoRa. That's about what in terms of short range data transfer technologies. That's about it. That's about the perception, the bottom layer. And next, it's about the network layer. Next, that's about what type of either in terms of network, in terms of mobile communication, or in terms of integration of various networks, we are going to look over it. So that's about the network. Next, please. So then application where the end user, like a medical information application, decision making. So in terms of whatever the medical records, as I said, MLI as a library information system. Similarly, the medical records are going to be kept as a very secure infrastructure where it is going to be accessed by whenever needed by the doctors instead of going for starting the testing from immediate, from the first time. So what is the history of the diseases, how it is going to be monitored. So anyone can, like a DigiLocker document, anyone can able to access our health record, but it will be very secure and very safe. So that's about it. Application layer in terms of decision making, what criteria, what I should take a decision, look over and diagnosis and second part. So that's about the different layers which is being defined over it. And next, the gateway layer where we talk about either you are going to use a GSM or whatever is going to be long range communication or in terms of a personal area network. So that's about the gateway layer which talks about it. And it's a framework layer. So that's once again the architecture. You can skip it up. So that's about, and this talks about the computing. As I said, once we are putting the every data are collected and puts on the store on the cloud, it takes much time to look over it and for processing and for accessing. In search, you can see that cloud analytics in terms of fog layer. So we talk now like edge layer, edge computing most overly in terms of minimizing the time instead of getting over clouds. So data are stored near the edge. It's easy to track and easy to observe the information instead of getting a long process or protocols to pass over it and get an approval. Okay, so that's about large volume real time data processing. That's about edge layer. Next one. So that's we talks about it. Edge computing, placing the data in the cloud so that the edge of the localized server where the data has been generated, so it is minimized, latency has been reduced for a smart devices application. Next one. So when I take for an example is given like a home care. So where not only for a patient in terms of temperature, in terms of the pulses, in terms of glucose or various parameters are measured, anything alarm is being given. So doctor is going to diagnose, he is going to reply over it. So it explains about various platforms or various layer, whatever it is, compared over it. Okay, real-time monitoring data. And as I said, we are having different types of IoT devices like in-home IoT, so like a patient in a home, and second one wearable on body. So whatever we wear on it, however you looked over it, like a person's body, like smartwatches, small pills, neuromodulation devices, or mobile IoT like cell phones using RFID tags or patches. Then public community IoT where a common place I can able to utilize and check my body like a weight machine or something else. I can able to record my data on something like a point of care kiosk, dispense medical devices, and in hospital IoT. So this is about different types of IoT devices like in-home, wearable, mobile, public community, or in-hospital IoT. Next please. So this is about the different images or with respect to IoT devices which shares over it. Next. So this is about the cloud computing. So the applications of 5G, enabler technologies. And whenever we talk about the big data, we have various V's. Okay, velocity, variety, veracity, volume, viscosity. So that's about various V's we look over it for big data. Next please. So this is applications. Next. So, and as when you are discussing that, the challenge is that heterogeneity. So the challenges of different parameters, how it is going to be compatible, like hospital information system, how the hospital record been taken care, and next one about laboratory in terms of tests, or in terms of images, radiography, sonography, or with respect to various types of images, how all those things like radiological equipment, like RIS, or with respect to picture archiving, like sonogram, or ultrasound. So all the different types, they can have different formats or different systems are going to be that how I'm going to integrate over all those things. So heterogeneity of health systems, that's to be taken care. And the challenges, whenever you're looking over it, so it is going to be very, very sensitive. Even though that we know when you want to measure our ECG signals, it is going to be very, very millivolt. So we have a small amplifier to pick it up over ECG signals, we go for it. So it is going to be very sensitive in terms of it. So that's about body movements. Whenever the changes in the body is how the topology is going to change, whether the parameters should not be affected, then the temperature change, any sudden rise in the temperature, whether device is performs, whether it is in operating range, which should not be a risk over it. Then about the very critical factor, energy efficiency, the size, the lifetime usability. Whenever you use a device, we should not use it or recharge it for often. So that when we use it, it should be a low power communication device so that it's used for a longer time. So it's about the size. That's what we call form factor. When it is very large or when it's not suitable for our wearable, so it becomes a very disturbing factor. We will not be interested to look over it. So that's about the size plays a major role. And how much range of distance it is going to be operated, range of transmission, as I said, heterogeneous environment, and over and above, the quality of service, what purpose it is meant, how it is satisfied, is there anything achieved or not. Then about the security, as I said, our personal data should not be taken for granted. As we get some more phone calls, like if you want a loan or something else, if somebody is getting 12th marks or admission, so goes on. So how the data of us should be more secured when it comes to an internet or whatever thing in the cloud. So that's about these parameters plays a major role in determining the challenges over the smart healthcare system. Whenever we discuss for IoT network design. And based on it, we just move on to next please. And challenges, the privacy, security, scalability, cost efficiency, compatibility, interoperability. Next please. So next about, you can just skip it. Skip. So the applications where we can wearable, that's about the startups and how much investments are they getting over it. Next please. Smart patient devices, you can scroll up. Watches, wristband, monitoring patches, others. Okay, so these are the healthcare companies which have been startups for recently for last 2-3 years from India. Next please. So next we want to touch about the 6G as we are now into era of 5G. How it is going to be in 6G, what are the expectations, whether we have not started using the full features of 5G, but now you can see that in few countries the research is going on about 6G and invention. So we touch about the parameters in terms of 6G, that's we call about next generation mobile wireless communication. We can see that an example is given, how long will it take to download 21 TB files. In 5G it takes 5 hours. In 6G it takes 18 seconds. So how fold it is going to be, you can see that. So here you can see in times, jitter, the delay, it is nanosecond. So here latency you can see 1 millisecond, it is going to be in 0.1 millisecond in 6G. In terms of error bit, it is one per bit. So it is going to be 10 megabits, the traffic capacity is 10 gigabits per square meter. So you can see the location, the user experience. So all those things are going to be in a multi-fold, which would have been expected how it is going to be in future. So how are they going to utilize it? Who is going to benefit all those things? So that's the next thing which is going to be looked over it. So that's a 6G. So whenever we talk about 6G, we'll be coming across few parameters, few things in terms of design, few things in terms of testing, few things in terms of standard. Whenever comes into new thing, the standards plays a major role. As we all across that, IEEE plays a major standardization factor which defines that this is the standard which you are going to follow it up. So that's about the extreme high data rate, peak data rate, extreme coverage, and low energy and cost, extreme low latency. So it is very less than 0.1 nanosecond and high reliability, massive connectivity. We cannot able to, now we can see some 100 users are there, it is going to be like 1 lakh or something, it's going to be, as how it is going to be increased. That's about the requirements of 6G wireless technology. So you can see you come across like ultra massive MIMO, small cells, whatever you see, device to device nodes, V2X. So it is basically about vehicle to everything. So when we talk about the connected cars, so when the devices gets communicated, like vehicle to vehicle, what we call V2V, then vehicle to infrastructure, what we call the vehicle to the, traffic signal, then vehicle to person, so vehicle to everything. So like we have a V2X, it's on different standards which is operating from vehicular technology systems and transport systems. So that's about V2X network, huge amount of research are getting over it. So that's about the cell-free and ultra-massive MIMO. So that's about the architecture which talks about it. Next please. So this is all the specification in terms of vision, in terms of technologies. You can see you just come across quantum communication, few things are getting over it. SAR is working on few areas of IIT. So research directions, it gets over it. You can skip it up. So this is about what we call intelligent connectivity. Whenever we talk about 6G holographic or deep connectivity or ubiquitous, so anywhere, anytime, and everyone. Just about ubiquitous connection everywhere, connection anytime, air, space, ground. Not nook and corners of the space. It should be getting connected. Ubiquitous computing we call over it. Next. So these are challenges which we call look over it, which is opportunities also we can say that. Whenever we talk about challenges, opportunities are there. Next. So this is about, we are discussed about network slicing now in 5G. So it is going to be a dynamic network slicing, DNS. So we talked about millimeter wave communication. Now since next we are going to look about terahertz communications. So next. Okay, so that's about the challenges which talks about higher energy efficiency, peak rate, data rate. Next please. So this is about the few data which has been taken from Government of India website on 5G emissions. Wherever we have some various factors are given. Next, you can skip it up. So this is the talks about Internet of everything. It's not about Internet of things or Internet of healthcare. It's about IoE, Internet of everything. It's going to be the future where connectivity in terms of all terms. So when we talk about it, it's going to be what to say, interdisciplinary in terms of communication, in terms of power, in terms of server, in terms of data, how it is going to be looked over it. Next please. So these are the research initiatives. As I said, from government 2020 document which has been taken, network design and architecture. Next please. You can skip it off. So this is about which I want to highlight about and share my experience with you. I shared this presentation with the institution. It's available in both PDF and you can just check out the references. A few videos are also there. And thanks for the opportunity. I once again thanks the management, PVR Institute of Technology and Science, which has given an opportunity for me to discuss and share my experiences. I hope this will take it to next level. Once again, thank the principal, HOD, the conveners, co-conveners, and the faculty team, and the entire students and press and media for giving the opportunity. If there is any questions I can discuss, because thank you.
Thank you very much, sir, for your enlightening session. It was very impressive, and the researchers and the academicians who are present in this session will definitely plan their research in the fields which you have shown, the new dimensions. Thank you very much, sir. Now I request Dr. Vikram Kumar Pudi Garu, Assistant Professor, IIT Tirupati, to present his technical session. Sir, please go.
Thank you. Good morning, all of you. Okay, before going to this, I really like that conference name, like ICRACE 2023. Okay, you have seen maybe like a more many people like a Vision 2020 like that. It's also like a race, like a recent advances in communications and electronics. So let me ask, why there is no 4G in 1950? Why there is no 5G in 1950s? Can any of you tell? First of all, why there is no cell phone that time? They have cell phone, but the name is like a radio man. Why do you think we don't have that? Can we go? So my name is, before you can think, we'll go into the details much more. So my name is Dr. Vikram Kumar Pudi. I did my PhD at IIT Madras. Currently I am working as an assistant professor at IIT Tirupati. My BTech, my BTech is from Narayana Engineering College, Nellore. I think Dattatreya Sarma sir, like when I was about to graduate, he became a principal for Narayana Engineering College. And you know Narayan Reddy sir, some of you. He taught a course for me like a digital IC design, okay, which is my prime research field like later, okay. Hello? Anybody asking question?
Murli sir.
Huh?
Sir asking Murli sir.
Murali sir.
Narayana.
Nellore. Yeah, he thought control system, I remember. Okay. Almost I remember most of the, except maybe 3 to 4th year, some courses like it. Rest of them I remember. Currently, like you can see that I don't have a master degree. Actually, many of you don't know that once you join IIT, there is a chance to upgrade to PhD. So that's why I don't have any MTech degree, master degree. I have only a PhD degree. Later, I did postdoctorate from the University of British Columbia and NTU Singapore. Now, assistant professor at IIT Tirupati. So this is my academic background. Today's agenda is like all of you know about computer, correct? And one simple question, I think many of you are from also computer science are there. You go and check your curriculum, the way the curriculum for computer science and electronics, the way they have designed very well. If you know the subjects from A to Z, you are able to design a computer. Computer means processor, like. All of you have smartphones, correct? And this has a processor. But the thing is, how many of the students able to do that? I am not saying that even at IIT also, students they are not able to do it. The reason, why do you think? What is the reason? The reason is what happens is, in the academics, like academics, we have worked on the computer and everything. We send to the industry. From the industry, nothing is coming back except the product. They don't interact with the universities or some places, especially in India I'm talking, but US is a different scenario. They will, the way they will teach with the industry interaction, along with the some faculty at the institute, they will work together and they will teach at courses. Not all the places at university, some places. But whereas you see that we are really lack that real time skills, real project skills. But the content is same. Whatever subjects we are teaching, they are the base concepts. But you ask them to design something, they don't have that. So we will discuss about birth of the modern computer. And after that, like since it is a advances in electronics, I want to talk about two devices. Like one is called quantum dot cellular automator, other one is memristor. These two things we will discuss briefly. We have, I think, time we will discuss briefly. Okay. So these are the few names like Charles Babbage is the one we call it the father of modern computer, correct? And how many of you know which is the first electronic computer? But before that there is something called ABC, computer. And next one is like a semiconductors and then integrated circuit. They changed our life. And the birth of microprocessor is what entire world is changed. But before going there, I just want to discuss about history. So this is the first one, like calculator. Charles Babbage, he invented a calculator. But how do you think that time multiplications and additions used to work? What is the logic? By the way, this is a mechanical. He is a mechanical person, he is a mechanical engineer, you can also. It's a mechanical computer. But what is the logic behind that is difference equation. Can you play the video? Actually, this one they kept, no, video. Can you play the video? Not,
ఆప్షన్ లేదు సార్.
Okay, Viva is not working, but actually they kept that one at a museum. If some of you are visiting UK, you can go and visit that. And this is the one of the relay computer, Cornell Juice. He worked at his apartment. He wanted to create something which can do the calculations. And this is also using mechanical relay. And what happened is, one of his friends visited him and he gave idea that instead of mechanical, why can't you use the vacuum tube? That time vacuum tubes used to use for communications, not for the computations. He thought that guy is a drunkard, he is giving ideas in a drunkard state. But actually the same time, this John Anathan from the USA, he got that idea. So whatever reason he got, but he wanted to use it vacuum tubes. This is the first electronic computer. And previously people are using based on logic system. They have moved from that logic system to base 2 logic system. When he is going for thinking and then he want to drink and he want to roam in the car, that time he got idea and he built the computer. And he never made any patent, he just left it. And 1967, some lawyers are approached because that time, which was the first electronic computer, and he never thought that this will be change the world. He never made a patent, he never got any money from that. But his work got so much recognition because of this. Like this is the first electronic computer, and it is based on the. In general, if you are building any project or anything, they will count in terms of total man hours. Basically, one person, if he works like 52 weeks, means 5 days a week, and 50 takes 1 year, he can do how many hours? 2000 hours approximately he can work. But imagine like 2 lakh, means 100 people continuously, they work for 1 or 2 years and they have achieved that, and it can perform 5,000 additions. Okay, per cycle. You know what is a cycle? Actually, that is called speed. 1 second, sorry, I think it is a 1 second, it can do 5,000 additions, maybe that time. So, which can very difficult that time to do by hand. Now, people have started using the vacuum tube and they are still like it was a lot of demand, but it takes like a lot of space like it. But is there any alternative for that? People thought. And one thing you can see that clearly is not like everybody knows about transistor invention. But same time, somebody could have invented some other transistor, some other diode, some other thing. Why do you think it happens same time, all that places? So that is where people will go to conferences, they will see somebody presentations, they will get idea and they will discuss. So my point is this conference also should be like this, like you should discuss among ourselves, any project is interesting, you should go, and also you should also attend lot of conferences in India. Maybe the registration fees for good conference in India will cost around 10 to 15,000 rupees. And maybe accommodation is what we have to look into. But overall, if you go, you will get lot of ideas. And he is working like it. He want to replace the entire vacuum tube with something. That something. That something it became like a. Yes. The something that is we call it as bipolar junction transistor, and that was the starting point of switch. Only the switch. Switch means it has 3 terminals, you can control like whether you can go to on state or off state. So, but that is only one idea. Next, there is one person. He is called Jack Kilby and Robert Noisy, but both are in two different industries they are working, not in the same. Okay, his idea is, why are you making transistors separately? Why are you making resistors separately? Why are we making inductors separately? Why can't you make a same material, capacitor, same material, transistor, same material, resistor? But that time the technology is not there, but he still worked to find a solution for that. And is any of you know how inductors are made into our ICs? Inductors. Usually they will make with a lot of wires, but if you see in our ICs, there is a usually the mass equations which is like a equivalent circuit from the capacitor, they will get it. The equivalent equations are what we will use in the inductor, but in general you see any IC we have resistors and capacitors and the transistors. That's all. We don't have more than that. We don't have inductor in general in our IC. Means processor, or you can take any, maybe in a remote also you have some electronics, other places. That is what. But same time you can see that Robert Noisy also got the same idea. He created an integrated circuit. But how these two people got? There is a starting point where they could have gone to some conferences, somewhere discussion, some research papers they could have read. So they came with that approach, and this changed everything. Next. So this is the first you can remember this 1966. This is the time you can call it as actual birth of electronics industry. This is where emitter coupled logic, single line, you don't need any other extra device, single circuit IC, you just have input and output terminals, they created it. And later, they went to processor. Intel is the one, 4004 is the working processor they have made. Like previously also they have made processors, but this processor is a completely different and a single chip. Single thing, you just have to connect it, it will work. So this is what is the operation of our processor? In 1971, 1 megahertz. What is the today's mobile operating frequency? 2 to 3 gigahertz. How many number of transistors this has? 1000. How many we have? Maybe 1 billion in our mobile. So this is all made it possible, but why it happened? Our lives, everything is like, for example, 1974 onwards, MOSFET. Previously we are using a BJT, but we replaced with MOSFET. What is a MOSFET? That is everything, we are not going technical. Our life is decided by this channel length. Everything, today's we are having the smartness, comfortness, and communications, mobile, everything like what Sar is talking about 4G, 5G is make it possible because we are able to shrink this. What will happen? It's basically like the same device but with less area. So you can check that one. The channel length, the more we are scanning, what is happening? It is becoming like a quantum effects came into picture. We are not able to create that as a switch. In I think 2010 onwards, they have funded lot of money. If you see the 32 nanometer, they have reached that time itself some problems. They replaced, somehow they are managed to MOSFET. Nowadays in our mobile, whatever you are using, 5 nanometer or 2 nanometer, they are not a MOSFETs. They are the FinFET. Even that is also going to reach the limit. So they have went into alternatives. So one of the technology is QCA. So basically, it works as a logic gate, but not by transport of electrons. It only use the electrons, if you place it two electrons side by side, what will happen? They will repel each other. Correct. By using that logic, they have created this technology, and the basic gate is majority gate. Next. I think the differences you can go through. I will share the slides. The MOSFET, you want to make a logic operation, you have to use the transportation of the current. But here you don't need. So this is a, if the electrons are diagonally arranged, anti-diagonally arranged, we call it as binary 1 or binary 0. I'm not going to give like full tutorial. This is one of the technologies. So this is the operations. While if you just apply a input, logic 0, it will be log. This is called logic 1. Next one. This is called logic 0. Like and next. This is a how while operation. Just to press one. Let's say instead of 0, I applied as a 1. So it will change the states accordingly that. So output will become 0. Similar inverter also you can check it. Just press it. If you apply a 0 and I will get output as a 1. But remember it is here they are not traveling. Okay. Next. So majority gate. You know what is a majority gate? In elections, who will win? Who gets the more votes? They will win. Correct? Correct or not? Yes. So majority gate, who is majority inputs? They will get the output. So two inputs are 1, so output is 1. So we will get output 1. This is called majority gate. By using this majority gate, we can make as AND gate and as well as this is a logical equation. You make one input as 0, it will become AND gate. You make it as 1, it will become OR gate. So our traditional gates also can be realized. By using this, you can do that. So the main challenging is realizing this circuit is very difficult. To work this, it won't work at room temperature. It should work at sub-Kelvin level or Kelvin level it should work. That was a drawback, but recently some people started fabricating room temperature quantum dots. Next. So actually this is not about telling me like what result I got. This is the one of the result. What I got is, we have that circuit, we have that equation, but with that we can only remove one majority gate. That is the first result. When I was doing PhD 2010 or something, I got that result. Maybe you can go to maths behind that, you can note down if you want. What is the impact of this? And many of you people are thinking, what is a research? Many of you are thinking that research will do for our promotion. Research means I am seeing like other person is doing PhD, so I should do that, or I won't get promotion, or some other thing like you want to increase your salaries or whatever. But majority of the things, when you will feel happy about research? My question. When you feel that when it is worthy to do a research, did you ever question that? The only time you will feel happy about the research, when you get a result which nobody gets in the world. You are the only guy who gets that result, how much small it is. That is when you will feel happy. That is when you will feel that research is a worthy thing to do. Okay? And whatever promotion, their salary increments or some other like a thing, all these things are byproducts. That is also very important. Okay? If you have some goal, then only you will do that. So this is the one, first 1 bit adder, means this is the one. I got it 1 inverter less. If somebody want to use like a 64 bit adder, 64 inverters are less in my design. is my first result I got. It got published also. This one I felt little bit happy. But this is only the first result. Next. So how you know about binary adders? Correct. All of you know about ripple carry adder and carry located adder. But prefix adders, there is a new, actually advanced version of that actually. They are much better than the carry located adder. You can see that the main thing is associative operators. This is the structure of the prefix adders. You can see that different variants, all of them main basic thing is prefix operator. Next one. So this is the existing prefix operator. It is based on that AND gate and OR gate. Majority gates we are using. But what I got is new prefix operator. This requires only 2 majority gates. It doesn't require AND gate and OR gate. By the way, this result I got after completing my PhD. Okay, I don't think anybody can reduce the prefix operator more than, because this required anyway 2 majority gates. So to get a small result, it takes more time. Don't worry about that. Sometimes how I got this result is, I was going through other people's paper, suddenly some kind of hint they have given there. I got idea from that, I could apply that. So you should utilize this conference like this. Okay. Somebody is using a different domain, different techniques, you should pick that one to utilize the conference. So with this, I have proposed a new majority gate based adders, which they should use, like if majority gate is the basic gate, instead of AND and OR gate, they should use it everywhere. So it anyway, this is 33% less area and 50% delay reduction. This is the layout QCA, the circuit looks like this. But some of the problems is like it to fabrication this. And why do you think the industries are not moving to new nanotechnologies? And to make a processor, that guy has to get a fabrication facility. You know, how many of you have idea about the semiconductor machine in India? Yeah. So how much money government is funding? 2 lakh crores something they are giving to who are going to set up. As a first installment, they have given 73,000 crores to somebody like. What is the, why do you think that much expensive that? No, but why fab labs are very, very expensive like?
To set up the clean room environment and various lithography techniques and deposition machines and...
Yes, the machines which she is talking, they will start very sophisticated, will talk from $500 million. To maintain that, it's even more difficult. On top of that, like for example, somebody comes with a 3 nanometer technology. We stuck at like only at the 5 nanometer. Nobody buys our processors. And we have to have an advanced research team like. All these things are there. Like, that's why you see that many companies sold their fab labs. But now they wanted to set up because of some geopolitical issues. So even this QC you want to fabricate, they have to discard like a tool, what is this, 100 this QC kind of technologies. Now you can see that quantum computing they are adapting. And quantum mission, any of you heard about quantum mission? Maybe communication, somebody working in government of India is going to fund 6,000 crores. They are already announced 6,000 crores they are going to give for quantum computer making or quantum communication or quantum logic circuit design. Some proposals they are giving that. Okay. Next. This is the one of the interesting one. Nowadays, our all of you have that RAM. Did you ever hear about DRAM? DRAM, SRAM, and pen drives. Correct, SSD. But next generation, maybe after 5 years, they are going to replace with the memristor, resistive RAM. So what is a resistive RAM is there is a correct, there should be element between the charge and flux. If you just vary the charge, flux also should vary, but there should be some constant should be there. That element is missing. And the he proposed that missing element in 1972. Nobody bothered to believe that, and he worked at the company. He still believed that there should be a fourth element. He started working, and 2010 he got that device. That is called memristor. That is where people have started believing that memristor exists. Right. It has a lot of advantages. One of the advantages is resistor with memory. You just apply some voltage. You just remove that voltage. It can store that level like resistance in the form of voltage, in the form of resistance. It can remember that. But what is the advantage? You can write, design a memories. But more interesting one is in-memory computing. Okay, you know when there was when they want to make a computer, how the computer architecture looks. How to make a, you can do addition, subtraction or something, correct? Some generalized architecture. The person who gave is Van Neumann. What he told, you want to do a computation, you should have separate for computation, means logic, addition, subtraction. Always you see that, what is the name you are seeing, SRAM. What is that other name is? Cache memory. Nobody bothers about that. Cache memory is the memory where it is very near to the processor. People, it is outside the processor. Even that is not the data, will go to our storage. Correct? But this actually removes that concept. Like even you can have a memory, like your pen drive itself, you're able to do the calculations. But they are slow. Currently, they are slow. How it will do is by using the read and write operations. So this is our proposed architecture. It's not a new thing. So this is the memristor element along with the transistor. We kept for energy efficiency applications like. Because the leakage is more, we came up with this architecture. 1T, 1R cell, which so we can represent like a high state, low state. So it will do, whenever you are reading, it will do the majority operations. It can realize a logic gate operation. That is where it will do the only read and write. But you can go, it is not required. So this is the architecture which your mobile memory or your pen drive uses this kind of architecture. So you can load the data to store the value. Reading, you can do the computation. Okay. How it will do is you can read the three lines together. It will form a majority operation. So this is the one of the work my PhD student she is working. So we want to make a generic prototype. Currently we are working towards that. So we wanted to go for beyond this, that is the computer arithmetic models we are already implementing, cryptographic applications and in-memory computing. Nowadays people are widely using neuromorphic computing. What is the, any of you know about difference between the neuromorphic computing and deep neural networks? Since it is advanced, I am not giving. Neuromorphic computing means it is our goal to find a circuits which will mimic the behavior of neurons. Whereas the neural networks means we will use the existing processor or something to do the mass operations, to implement a neural net. So this is what our future work. If you have any questions, you can ask.
Do you have any questions? This is a very good opportunity to interact with the professors directly. If there are no questions, we will conclude the session and break for lunch. Sir, Vikram sir, thank you very much, sir. You gave.
Once again, thank you for giving this opportunity for ICRACE team. Great thanks to them and then give big hand to them. I think.
Thank you very much. Now it's time to say bye to this inaugural event. I request Mrs. Manrekha Madam to present vote of thanks on this.
Distinguished guests, respectable invitees, and my dear colleagues, it's my pleasure extending vote of thanks on this graceful occasion. Firstly, it's my privilege to thank the chief guest, Dr. K. Vikram Kumar Pudi sir, for his inspiring presence in this event. Sir, we are very grateful for the valuable talk, which is really a source of inspiration for all of us. We are extremely thankful to you for being with us today. I extend my sincere thanks to the keynote speaker of today's event, Dr. Vijayendra Babu sir, for his presence. Sir, we are grateful for your talk about the IOMT, core essentials, interdisciplinary approaches, professions, etc., which is really a source of inspiration for all of us. Sir, thank you for inspiring us today. My heartfelt thanks to the management for being a constant support for all of us and encouraging us in our professional growth. I take this moment to show my gratitude to the management on behalf of the Department of ECE. I take pleasure in extending my sincere thanks to our beloved principals, Dr. B. Dattatreya Sharma sir, Dr. T. Suresh Babu sir, Vice Principals N. Srinath Reddy sir, Dr. V. V. Sunil Kumar sir, Convener Dr. R. Sravanti madam, co-conveners Dr. M. Venkatesan sir and Rasvi sir, and the whole organizing committee of this conference. I am glad to thank the controller of examinations, all the HODs, invitees, technical reviewers, participants, and my dear faculty who made this conference possible today. Finally, once again, I thank you all and have a great day.
Thank you very much, Rekha Madam. Now the session we will break for lunch. After the lunch, the technical sessions will happen. The technical sessions are divided into two, like offline mode and online mode. The participants who have physically have attended will be giving the offline presentation here in the same place. This is the venue. And the participants who are participating from online will be joining us in Google Meet links, which have already been created and communicated to them. And we'll start the sessions at 1:30. Okay, thank you very much. For online the session will be, for offline the session will be at 2:30. Okay, thank you very much. The venue for lunch is dining hall in the hostel. All of boys hostel. All of you can go and have lunch there in the dining hall of boys hostel in our campus.